Okay, great. Thank you everyone for showing up to this Amy seminar. For this week, we have Max Kiss from CWI. He's a PhD student there, working on deep learning and CT imaging, as we'll find out right now. So take it away, Max. Thank you for being this week's speaker.
Thanks for the invitation. And as requested, I give a brief intro also on my background for the people that haven't met me yet. So I studied physics for my bachelor's and master's at ETH in Zurich, and did my master thesis in the US, actually, at Stanford University. And then I started at the institution that you just mentioned, the CWI, which is the National Research Institute for Mathematics and Computer Science, in 2020, so directly in Corona. And then, as you can also see and saw on the headline, on the title slide, I did 2 research stays in Cambridge at the Cambridge Image Analysis Group of Carola Schönlieb, which was the time where I mainly conducted my research that I will present to you today. That is like the academic side, but I also want to emphasize for all the people that do academia, but also are not that yet stuck with academia or advanced in academia, that there's other things that you can do in life as well. So I did a lot of things in business as well, working for a youth education company, starting my own social startup, working as a rhetorics coach, and doing a lot of other things like ETH Model United Nations, mentoring people, joining in presentation competitions. So I really, really encourage you build your scope, build your skills in all these other areas as well, aside from academia. That is really important for later. But now let's dive into the actual topic of the talk, which will be about computed tomography. And for those people that have not yet an idea what that is, I will just give a brief introduction and also give a few basic terminology explanations at the beginning, that we all have the same kind of wording that we use for the rest of the talk. So it's a non-invasive imaging technique for patients that you know best probably with the medicine application or objects. And there are sometimes peculiar shaped objects that are carried to our institute, and they ask, oh, well, what is inside that? How is that made? And you can take a few X-ray projections, but that is not that insightful. But if you do a 360-degree acquisition with X-ray projections, and then you can reconstruct a cross-sectional image. So this is the terminology that I will use in that. But we can also do that not only in 3D, but we can also do that in 2D. So let's look at 2D computed tomography, something that I mainly do with my research. And yeah, one of the scanning objects is the sample tube. Many of you might know that from presenting at a conference and carrying their poster there. That was actually what gave me the idea to study this in that way. And we have an X-ray source on the left, and that radiates through that sample tube, and we get 2D X-ray projections. If we only read out that middle, that red detector line, we have a 1D line projection. And if we acquire loads of these to 360 degrees in such a laboratory CT scanner setup, we will get a set of 1D line projections, which we call a sinogram, based on this sinusoidal wave form that you have in the image. And out of that, we can again reconstruct a slice, a cross-sectional image of our object. In this case, you see already an image of this sample tube that has been imaged in our FlexRay scan. That's for basic terminology, but why do I show you this, and why do we talk about acquiring different scans at the talk about learned algorithms and AI? Well, if you look into the recent efforts in computational imaging to apply AI, ML techniques for tomographic image reconstructions, then you know, or should at least know, that realistic experimental data is scarce, but very, very important to do that. One of my Stanford professors, Andrew Ng, always said, well, if you have not the correct data to train your machine learning algorithms, your machine learning algorithms will always fail. So if we look into the field of computational imaging, what is out there, There is the fast MRI data set, many of you might know from Facebook AI and NYU. There was the low-dose CT grant challenge of the Mayo Clinic. There's also things like the Lodopop from University of Bremen, or another data set of our institute, the Walnut data set for cone beam CT. But when we assess these different data sets, we realize that, well, many of them have only a very small sample size, or they only based on simulated projection data, or they have just limited application possibilities. So they only have simulated noise, or they target cone beam artifacts, or at least for me, have the wrong modality because I'm not an MRI researcher. I study CT, so the fast MRI, although a fantastic data set, does not really work for me. So, well, if you lack a large 2D experimental data selection, and that is a big disadvantage to do machine learning on 2D CT, you could do one thing, and that is acquire it yourself. And that is the first part of my PhD. And I want to allude a bit on that because it is very important to think about these kind of motivations, how to design your experimental acquisitions to then enable actually the machine learning that you want to perform afterwards. Three major challenges for that. First, most research groups do not have a scanning facility available, so you can't use that for large-scale, time-extensive data acquisition processes. Most available scanners are only like very limited way adjustable with their acquisition parameters, their geometry, especially for your applications of medicine. I guess you're just stuck with whatever the machine offers. Sometimes you cannot even access any raw data or anything like that, which limits the ability to acquire the data set, but also the applications. And most available scanners cannot be optimized. And that is very, very much important if you want to have large-scale data sets, which are necessary for deep learning. We're talking about thousands and thousands of slices. If you can't optimize the process, if you always have to manually release that scan, it's going to be very cumbersome, and you cannot end up with a high number of CT slices. We have the Flexor scanner in our institute, within our group, the computational imaging group. It's highly flexible. You can adjust a lot of parameters, and it's also scriptable. And that was our advantage to like plan and acquire CT scans independently using scripts and adjust these in all these different parameters. Now, we know what we can use for acquiring the data set, but what should the data set look like? What do we actually want to achieve with it? What kind of aims and requirements do we have for the collection? Let's have a look. One thing, we want to release raw experimental data. We did not want to rely on artificial data, simulated projections that have varying degrees of realism. We want to have the raw measurements released as well. We also want to look at real-world applications. So again, your case, medicine, medical CT scans. We want to have similar image features and contrasts as an abdominal CT scans. And we want to have the possibility to still expand that afterwards with like other multi-class segmentations or different kind of samples, that everything is like very reliably reproducible. And we want to have different application areas. And that is again the connector with, oh, what do I want to do with my machine learning data collection, with the 2D CT data collection? Well, we wanted to do denoising. We wanted to do sparse and limited angle scanning. We were thinking about beam hardening reduction, super resolution, region of interest tomography, or even segmentation. When you have all these in mind, then you can start planning on how do you have to acquire the data, what does the data need to offer you to be able to implement these kind of machine learning algorithms. Let's look at the three key features for this acquisition, and then I will quickly walk you through that. First one, we need a scanning object and a sample mix. We need a scanning setup and experimental design, and we need a semi-automatic data acquisition to do that. Scanning object and sample mix, just quickly, we wanted to reproduce contrast and features of abdominal CT scans, so we were thinking about different shapes and objects. They are diverse enough with like a high natural variability in both inter and intra sample shape and density. So like walnut will always look like a walnut, but no walnut is like another walnut. And it's more like diverse than, oh, we have styrofoam balls of like 0.5 millimeter diameter. And well, if they're produced well enough, that's always going to be the same. And the machine learning algorithm doesn't learn shit. It only learns, 0.5 millimeter spheres, and that's it. So that was one requirement, and that it's stable enough over a long scanning time, because we radiate this with a lot of power over a long duration, and gets hot. We filled this cylindrical cardboard tube representing the body, let's say, with centimeter scale objects, mimicking organs, bones, and that were dried fruits and nuts, and they were all submersed in a background medium resembling the connective tissue. And banana chips, dried figs, raisins, you name it. It looked like a cooking class, but it actually had a motivation because we wanted to have different classes of densities, something that is like more dense and humid, like dried figs and raisins, and something that is lighter and has different kind of shapes like almonds and walnuts. Almost the same density, but a completely different substructure. And if you can have all these different features, different samples in your slices, you can also train your machine learning algorithms to learn diverse shapes and densities, and not only like one of a kind and always the same. Then let's jump to the next one, which would be the experimental design, the scanning setup. We want to have these application areas. I mentioned them earlier. And I will highlight now a few things and tell you that the green things we can basically have for free. If we acquire our scans in a high enough resolution, both spatially and angularly. So let's have a look. Let's determine the number of projections that we need with the Nyquist-Shannon sampling theorem applied to CT scanning. That is like the amount of projections, the length of the detector line times pi half, and you end up with like 3,000 projections roughly. So we oversample them that 3,600. That's the number of projections that we want to take. But we also have to look into the geometry and how we can image that. So if we choose the positioning, we want to have sufficient photon flux, we want to have high resolution and a good detector coverage. So if you now look again at the different sample, the two guiding parameters are SOD and STD, the source object distance and the source detector distance. With that, we can determine like what happens with our scan. If we increase the STD, we get a more parallel beam geometry, but also the photon flux decreases and we have higher noise. Again, bringing it back to the application of medicine, if you acquire with a too low photon current on your machine, if you have too short exposure times, suddenly you have less photon flux and you have higher noise and the data is less interpretable. So for like an optimal scan design, we want to minimize the noise. And therefore, like we could increase the scanning time, but that also increases the data acquisition time. So we're kind of like stuck in well, what kind of way do we want to walk? With determining a magnification factor and a resolution of the scan that we want, we ended up with something that covers the detector just about, like with a bit of a leeway on the sides, and maximize the spatial resolution with that while still having a close enough setup to have a high photon flux and not too much noise. We ended up with something like 61 micron. Again, bringing it back to medicine, you usually would have like 300 to 500 micron resolution in a normal medical CT scan, but also your phantoms, your bodies are much bigger. So you would have like a diameter of, let's say, 60 to 120 centimeters. And our object only had a diameter of 10 centimeters. So as we scale with the fivefold in our phantom, also our resolution is a fivefold, smaller than the medical application. All right, so we determined those two things. We're well oversampled in the angular projections and with the spatial resolution, and therefore we get these screen applications for free, but we still have to take care of the red ones. So we need to acquire something that is noisy if we want to be able to do denoising, but we also need something clean, because otherwise, what is our matching data that we want to compare it against? And we wanted to have something that has beam hardening artifacts, because we wanted to do beam hardening reduction. So yeah, how could we do that, that we have all these kind of application areas, especially the beam hardening artifact inflicted one, that was something hard to think about. And what we ended up doing is we looked at the beam spectrum, and we know that there's an energy dependent absorption. And well, if we do place materials into the X-ray beam, usually metal sheets, we can reduce the low energy portion of the beam, or pre-hardening the beam. And yeah, you see a few simulated beam spectra there. And if you look at the blue curve, that is standard 90 kV tube voltage standard beam spectrum. Now, if we have the same spectrum, but use a so-called Torreos filter, it's a compound filter of tin, copper, and aluminum of these thicknesses, we suppress this low energy photon range, and we basically shift the mean energy of our beam spectrum to around 60 keV, and that will lead to less beam hardening artifacts in our scans. And comparably, we have the 60 kV with no added filtration. There, the mean energy is around 30, 35, and a high, low energy portion of the photons, they will get stuck in the object. The flat field and dark field calibration will lead to artifacts, and voila, you have two different ways to acquire the data, one that will have beam hardening artifacts and one that doesn't. So modes that we acquired our data with: one, noisy, 90 kV Torreos filter, but only a very low tube power, 3 watt. Mode 2, the clean one, 30 kV, 90 kV, 90 watt with a Torreos filter. And mode 3, the artifact slice, 60 kV, 60 watt. So no noise because we have high tube power, but without the filter, we have artifacts in terms of beam hardening. Okay. This is what it would look like, just to give you a quick overview. You have 1, the X-ray source; 2, this filter sail that we had; the rotation stage; 3, 4, the sample tube; and 5, the flat panel detector. And we switch between this mid position and front position within the acquisition to acquire ones with and ones without filtration. And how we did that, you will see in a second. We wanted to scan this slice by slice. So with the 1 millimeter separation, we always move down detector and source by a millimeter and by another millimeter, and therefore imaged different slices in our tube. Because we only read out the middle detector line of the, one of the first slides, the red one, we basically have a fan beam acquisition setup, and we acquire in 2D CT data. And each of the slices were scanned in these different modes. Now, last one, before I will get to the more applied deep learning part, how did we acquire the data? We needed to, let's go for the legend first. We need to acquire both dark fields and flat fields and line projections of every single slice of the tube, and in all modes. So we started in the front position and acquired a pre-batch dark field, a pre-batch flat field. Then we started to do the 3601 projections, line projections, while the object was rotating. We move down a millimeter, we take the second slice, down a millimeter, third slice, and so on and so forth, until we are at the 10th slice. We take the post-batch flat field, we switch the parameters, so we increase the power of the tube from 3 watt to 90 watt. And then we acquire the same slices. So it's very matching. And that's the important thing about machine learning here. If you would not have matching data, you would certainly learn transformations of your object. But since we have not moved the object, we just reacquire the whole thing, but with different acquisitions, we have matching slices just acquired in a different way. And again, slice 1, 2, 3, up to 10, and then switching to the mid position with mode 3 without beam filtration and with 60 kV and 60 watt to get our last mode acquired. And that goes forth because like 10 slices is not enough, and like 11 to 20, and like we batched it that way, like always in batches of 10. And we acquired actually like complete batches of 50 in one scanning session, usually, sometimes 40, sometimes 20, like depending on how much the scanner was available, but usually 50, which lasted 8.5 hours. So in 111 sessions, we acquired in over 850 hours, 5,000 slices over the duration of 5 months. So it's very handy that I live basically 3 minutes walking from the institute, because I was there a lot. Every day and night, changing the tubes, setting up a new scan. 540 million files later, because we're talking about deep learning, so a lot of data, we ended up with the 2D tag data set. We combined those two 3,601 times 1,912 sinograms, because I don't want to deliver 540 million files to you if you want to use that, and created also iterative reconstructions with non-negative values and 4-class segmentations from those clean reconstructions, that people that do not have these high computing facilities available can actually use the data set also just like that, downloading the sinograms, downloading the reference reconstructions, and doing machine learning with that. All right. Quick visual overview that you actually understand what you're getting. You're getting the raw projection data, sinograms, you're getting these iterative reconstructions, you get the segmentation that is a reference, and you also get the scanning geometry and the pre-processing and reconstruction and segmentation if you want to use the 2D tag data set. And now we look into the specific slice and what we now can enable with our machine learning. So slice 1, very grainy image. Here again, the parameters that we acquired it with. I removed the background for you to make it a bit more visually pleasing. But yeah, it's an artifact-free image in the sense of no beam hardening artifacts, but you have a high noise. Then there's the clean slice. So again, the parameters, artifact-free, low noise, very crisp image. You can do a lot of things with. And the artifact slice, and you now already see like the heavy shadowing and streaking of the beam hardening of the high attenuation objects. And we have beam hardening artifacts, but there's not any noise present, very low noise acquisition. Based on this second mode, the clean mode, we also created, there you go. A 4-class segmentation, so filler material, background, tube wall, and then the objects inside. You can scale it up, but like doing a 10-class segmentation with every single item, is that a fig, is that a walnut, is that an almond, and so on, was a bit too much for this project, but we invite people to amend that. And suddenly, with all these different images, we can have versatile deep learning applications. So let's recall again, what did we want to do? Well, we want to do reconstruction and segmentation, maybe even of limited or sparse angle sinograms. So only taking like the first 90-degree projections, 900 projections, or only taking every 10th or every 20th line of the sinogram and see if we can still reconstruct. So we want to end up this and maybe even create a segmentation. So going from there to this and this, or maybe even both at the same time, would be something that we would be interested in. Another one was the low-dose CT reconstruction challenge. So we pair the high noise and the low noise data. So make that big again. We have the high noise slice, and we match it. We do supervised learning, pair it up with the clean slice, and suddenly we can denoise on a machine learning rate. And lastly, removing beam hardening artifacts. So now taking this beam hardening afflicted slice and mapping it to a beam hardening reduced cleaner slide, and again doing that with machine learning was the objective of our data set. And the data set is described in this paper, and you can scan the QR code if you are interested in using that. I will pop that up later as well. But that's now the basis. And we can now think about actual reconstruction tasks that we want to do. So full data reconstruction, I just take the whole sinogram and put the iterative reconstruction slices as a target. Or I take only a cut down version of the raw projection data of mode 2, so the clean mode, and only take like the 120, 90, or 60 degrees and try to reconstruct well with that as well. Or I take sparse angles. So we tested different levels and figured out the more challenging and suitable ones are like 360 projections, so only like 1 degree separation, or even less, like every third degree, every sixth degree, acquiring a projection. Suddenly with that cutout raw projection data, the reconstruction gets much more difficult. The low-dose reconstruction I mentioned already, and also the beam hardening correction reconstruction, that is something that we can just do by mapping the different modes. So mode 1 raw projection data mapping to mode 2 reconstructions, or mode 3 raw projection data to mode 2 reconstructions. Again, mode 2, the clean one, is always our target because we want to clean things up. How does that look like, and what can we do to benchmark then machine learning algorithms on that? This is a visual overview because, well, what does limited angle artifact look like? What kind of problems do we run into? I guess many of us have not seen that at all or much in our studies or in our research. So here, visualization, full data, everything's nice and clean, limited angle, here 90 degrees. You see how you're like losing boundaries. You have streaks following these like 90 degree that you're missing. There's sparse angle where you have basically a star-like pattern because you're missing information in these directions in your data. And here again, like grainy, noisy image and a beam hardening afflicted image. If we have all these tasks, and we talk about benchmarking, we're talking about, well, there's a like broad variety of methods out there to solve these inverse problems with data-driven models. Usually you would classify that with something like post-processing networks, learned iterative or unrolled schemes, learned regularizers, or plug-and-play methods. It's like the general categorization that you can do, for example, for data-driven models for CT reconstruction. But if we talk about any studies that investigated these different methods on CT data, usually they lack comparability. They use data sets that are not openly available, or they use data sets that utilize a lot of simulation, or data sets with various sizes. So maybe you operate on the same Mayo Clinic data set, but somebody takes like the first 60%, the other one uses 80% of the data set to train those things. Or they just like take the regions of interest in the scans that they want to focus on and drop all the others. Suddenly the different methods become less comparable. And they might even use different preprocessing pipelines or different model implementations. And well, with all of that, there is no comparability. There is no fair assessment which machine learning algorithm is actually good enough for it. So if we look at this list, the first three, you now know from the first half of the talk, we can easily solve with our 2D tech data set, because that is standardized data, and that is acquired, it's openly available, no simulation, and it's clearly defined how much of it you can use. And for the second part, I went to Cambridge and got in contact with Anda Biguri, who implemented and developed the Lion toolbox, Learned Iterative Optimization Networks. And that is a big toolbox implemented in Python that you can use deep learning methods on CT data. And there is standardly already available the LIDC IRI, I think it's called, or IRL dataset, so the long nodule dataset that is publicly available. But now also we implemented data loaders for the 2D tech that you can use this toolbox and all the methods that we've developed for this benchmarking on all the different deconstruction tasks defined and loaded for the 2D tech. And well, if you do this benchmarking and we look in these different model categories, we have post-processing, learned iterative, learned regularizers, and the plug and play. We implemented 3 each for the categories to have like a bit of an overview, but that's not guaranteeing any completeness. It's just, well, we selected some because we need to. And we selected the UNet, the MSDNet, and the DNCNN after an FBP, basically just post-processing of a bad FBP outcome of a bad data, be that because it's limited or sparse or because it's noisy or whatever. For the learned iterative methods, we used learned gradient with a TV regularization, and the learned primal dual algorithm. For the learned regularizers, we used adversarial regularizer, adversarial complex regularizer, and TDV. And for the plug and play methods, we use DNCNN PMP, DR unit PMP, and the gradient step PMP. And the authors of the code are Anda, of course, developing the toolbox, myself and Ferdia, mainly for the plug and play methods, and Zach for the learned regularizer methods. Okay, now you have all the information of like, what data do we apply to? What models do we use? What tasks do we want to solve? Now, if you actually want to do that, I already said we had to select some. Why? Well, because that table is basically 1 year of GPU compute. We blocked the servers at our institute for 3 months, and we have like 15 GPUs there, 20 GPUs roughly. And they were all computing nonstop during the time to get this big overview. So again, you see the columns to just give you a bit of an overview of the different CT image reconstruction tasks. So full data, limited, sparse, low dose, beam hardening, and all the different categories of deep learning, but also classical methods that we wanted to compare against. And all of them have been assessed with structural similarity index and the PSNR ratio. Well, numbers don't tell much. Images do better, probably not in that size. So we will look at a more zoomed version of this later. But just to give you an overview of what does it look like and how big and actually insightful this comparison is, if you look at all of that for one slice and suddenly see how well these algorithms are performing. Here for a first example, we have the FEP unit on the beam hardening task. And that is additional material, so not in this big overview. This is basically on our test set of the 2D tech. We use the minval, so the minimal validation loss model on our validation validation set of the to detect and applied it to the test set and looked what slice within the test set is performing best, worst, and close to the mean being reported in this big table. And you can now see how well you're performing well for the FPP unit, beam hardening, for the best slice, 0.86 structural similarity index, pretty good. But if you took a look at the worst slice, then 0.31, that is already fairly bad. So the FPP unit is not too good to sort out beam hardening artifacts. Let's look at other tasks. The FPP unit now for the limited angle tomography and also the full data acquisition. If full data, everything's nice and clean, you don't have much problems. But if you look at the limited 120, you already see artifacts popping up in the missing data regions. It is performing better. Here you see it 0.5 for the worst slice even on this task in comparison to the beam hardening, but it is definitely a challenging problem. Your mean result is like only an 0.72. And that task gets more challenging and more challenging the more reduce the wedge of data that you have available. So for a limited 90, you're getting worse, limited 60. If you look at these reconstructions, even after like applying the unit, well, the data is really bad and you're off by a lot. For the sparse angle reconstruction, it is performing quite well. So for the best slice, 0.92, like really good score. Even for the mean, 0.74, for the worst, 0.39. That's kind of good. We see that you're able to remove these streaks and graininess mainly. That works well for this case. You see in the error distribution that it's getting harder and harder the sparser you get to remove this, and the error is also distributed along the star lines for the standard artifact that you would have with sparse data. And yeah, for sparse 60, only having 60 projections. That is a very challenging task, but you're still doing quite good. The post-processing method is able to do that well. Standard denoising, also a fairly good task that you can do. Why do you not get similar values like for sparse 60? Well, because in the low noise, in the low dose acquisition setting, you also experience a lot of photon starvation. So maybe you don't even have any measurement and you have streaks that are much harder to remove than if you afterwards sparsify the data and therefore lose photons and make the data also, let's say, noisy through sparsity. That was the overview of the FPP unit. I will not do that with every single other method that we did because, well, you've seen 4 categories for each. That's going to take some time. But what I want to highlight is one of the most challenging tasks and give an overview on that over the different methods. Each only like one method of each category to make it a bit simpler. So here we now see the limited 60 case. You already seen this now with post-processing. Now we're talking about PNP methods, the learned regularizers, and the iterative unrolled schemes. And you see a massive difference. Well, PNP and ACR, although the best in their respective category, they still suck on this data. They are not designed for in-painting tasks like filling in missing data that you do not have in your raw projection data. They can mitigate the problem. You've seen how bad it actually looks if you just do an FPP of this, but not that well. But if you look at the LPD, the learn primal dual, it's kind of mind-blowing how well you perform. Like even for the worst slice, you have an 0.5. A mean of 0.77. If if you look at this data, you would not even assume that basically 270 degrees of your projections are just missing. So if there would be one hard conclusion on this benchmarking, it would be that learn primal dual outperforms in almost every task all other methods. And it doesn't mean that like all the other method categories and all the other methods in those categories are bad. They have their merit. Sometimes some of them are much easier to train. Some of them are less computationally intensive. Some of them work well for some categories, but not for others. And then you can use them for those. And you can see the details at some point in the paper when it's published. But overall, if you just want to make a decision on which learn method you want to implement for CT reconstruction, I highly encourage you to use the learn primal dual because it will perform well. So to give a last overview, last summary, our 2D tech data collection enabled various supervised learning applications. You've seen them already. If you want to access the paper that describes the 2D tech data collection, you can scan the QR code. And this is the benchmarking of learned algorithms paper that currently is in review. I would have loved to put another QR code there to let you scan that and read about it, but I hope this is out soon. And yeah, the last call that I can make is that standardization is of vital importance, and please do look into your data when you want to do deep learning, because the better the data, the better your model is going to be. And if you want to do that for computer tomography, the 2D tech data collection is a good starting point. And if you want to reach me, if you have any questions, you can email me with mk@cwi.nl, and I'm open to your questions.
Great, let's thank Max for a very interesting talk. Please go ahead and unmute for a question or type it in the chat and I can read it out.